Hi, I'm Derek, and this is DC to Daylight, where we explore electronics in the realm of DC, audio frequencies, RF, and into the visible spectrum of light. In today's video, I'm going to take a DC power supply that I've been working on over the past few weeks and create a 13.8 volt regulated power supply with peak current handling capabilities up to 30 amps. So I've got a bunch of parts that I had laying around for years, and I'm kind of Frankensteining everything together. I have an AC power source that I don't really use and I was doing some experiments with, and I no longer need a lot of those components. So I'm going to take the enclosure from that, take the DC components and put them into that, and we're going to apply the knowledge that we used in Zener-Regulators in the previous episode, apply them to this one, and we're going to regulate the 25 volt output of this DC power supply down to 13.8. So if you're interested in regulating voltage with Zener diodes and op amps, this is the place for you. Let's get started. Here's a peek inside the power supply. I have two toroidal transformers here. And the reason that I didn't go with one is because it would be massive. So I can actually split the current between the two, connect them both to the AC mains. The issue is we need to use some inrush current limiting components on this side for both, which makes the wiring a little more complicated. Both of those transformers go through two sets of full wave bridge rectifiers and they combine here after all of this. Now, I don't recommend doing that because there are some special considerations that you need to take into account, like circulating currents and phasing and things like that. That goes through this 50 microhenry inductor. Typically with a linear power supply, you'll see an iron core. This is an air core. I use this just because it has a high current capability and I have a lot of these laying around from other projects. That goes over to 160,000 microfarads worth of capacitance. That goes to the front pins, which you can't see, okay? We'll look at that in a minute. But what's wonderful about this enclosure is there's this wind tunnel, and this is going to contain our pass transistors. So this guy mounts in here like that. We have proper airflow over this. This is just a spare one in case I need more current, maybe in the future. But what I really love about this case is that on the front panel, we had a circuit board that's mounted in this slot. And I can take this out, unplug this connector on the board. So I've just simply replaced the board that was in there with my own blank PCB that we can prototype on, which is fantastic. It's got a built-in heatsink for our driver transistor. And I'm going to build the op amp over here somewhere and then leave some space for additional things in the future, like over voltage protection, over current, and thermal protection. So pretty cool that I don't have to take this thing in and out of the rack. I can just modify circuitry and plug it back in. And there you go. So now that we've looked at the power supply's individual components, let's take a look at a block level diagram so that we know what we need to do to get that 25 volts down to 13.8. Okay, so here's our block level diagram of just a basic run-of-the-mill power supply. Okay, we have a voltage step down from our wall to whatever voltage we want. Okay, that still remains AC throughout there. Typically we have some kind of a rectifier circuit that takes that, turns it into a pulsed DC waveform. Then we filter that out, which kind of fills in these troughs within our pulsed DC output. Okay, and then if we're going to use this as a regulated power supply, which is what we're going to work on today, we add this additional block here, which is going to give us a stable regulated voltage, nice and flat, hopefully. So let's take a closer look at each individual block. Now, typically here in the US, we're operating at about 117, 120, sometimes more volts RMS. Anyway, we want to step this voltage down to something that's more usable. To do that, we use a transformer. All right, so whatever this winding ratio might be, we can lower the voltage and increase the current capability. In this case, I have an 18 volt RMS secondary, and I have multiple transformers, as you'll see. But if we calculate the peak voltage, which is important to us from here on out, we take our voltage RMS, multiply it by 1.414, and that gives us our voltage peak, which is about 25 volts. Then we go on to our bridge rectifier. So what this guy does is forward biases a couple of these diodes on one half of the cycle, reverse biases those and forward biases the other side, and this bottom section actually gets flipped up. So what we end up with on the output is a pulsed DC waveform. Now, since this is a full wave bridge rectifier and we're flipping up this bottom half, our 60 hertz coming in, which is the frequency of our AC waveform, gets doubled. So now we have 120 hertz. This is very helpful in decreasing the amount of capacitance in the filter later on. So now how do we get this to be a nice flat DC voltage? Well, we have to kind of fill in these gaps where these troughs are. And that's the job of our filter. So there are a number of ways that you can filter this pulsed waveform to get a flat, stable DC output. We can use an RC filter, we could just use capacitors. In the case of our power supply, you'll see that I'm using an LC filter to give us a relatively flat output. And the waveform that we end up with, we charge up these capacitors on a positive going pulse, and when it starts going negative, these capacitors start discharging into our load, which leads our voltage to drop, and increase and drop, and increase and drop. So we end up with this ripple here. Okay, we want to get rid of that. Depending on the application, it's not so important, but I want to get this as flat as possible with the components that I have. Typically, that's where we would stop if we had an unregulated power supply, and that's what I've built up to this point. But now we want to add this Zener-Regulator circuit. We'll talk about this more in depth, but we have, just like we talked about in the last episode, a Zener diode that's reverse biased, and we're going to operate in its reverse breakdown region. This will provide a voltage reference to an op amp. Then we're going to compare at the output of the power supply against that voltage reference. That will all control a series of pass transistors that handle all of the current. And what that's going to do is we can adjust that kind of like a valve on a water faucet, okay, which allows a certain amount of voltage to pass through. So we can regulate it from 23 volts down to 13.8 volts. Okay, so let's overview what we're building today. So we've looked at so far this portion of it. We're done with that. All right, we have a voltage coming in, and then we have a Zener voltage circuit as a reference. Here we're using 6.2 volts. That's going to go to the non-inverting input of our op amp. Our op amp is going to act as an error amplifier. So we're using a reference and we're going to sample the output, okay, between that and ground. And any difference between the inverting and non-inverting input is going to show up at the output, which will control a driver transistor and a bunch of pass transistors that are all connected in parallel. And that's going to help distribute the amount of current and heat, okay, from these pass transistors as they kind of turn on and off to limit the amount of voltage that shows up across our load. All right, this resistor is our load. First off, let's look at our Zener circuit. So our supply voltage is going to be about 24 to 25 volts. We need to set this resistor value to force a certain amount of current through this reverse biased Zener diode. And if you recall from the previous episode, we want to keep this operating point in the reverse breakdown region of the Zener diode. So we need to put enough current through here greater than the minimum current in the data sheet around the test current of the data sheet and not to exceed the maximum amount of current. So refer to your data sheet. I want to put about 20 milliamps through this thing because I know that's a nice safe value, and that gives me a power dissipation of about 1/8 of a watt, which is well within what this Zener diode is that I'm using. It's a 6.2 volt Zener, and we'll talk about why I chose that in a second. But to calculate the amount of current, we need to take the supply voltage, subtract the Zener voltage to get the voltage across the resistor, and divide that by the resistance itself. So in that case, it's 25 volts minus the 6.2 volts across the Zener divided by the 1 kilo ohm resistor. That gives us 18.8 volts divided by 1K, or 19 milliamps. And of course, that's Ohm's law. The next part we should take a look at is the closed loop nature of this non-inverting amplifier that we're using. So this is basically an error amplifier, and we're using 6.2 volts as a reference point for everything else. We're sampling the voltage across the output from the Vout terminal to ground. And we have this voltage divider network here, and that is fed back to the non-inverting input. And what that means is that if the output voltage decreases for some reason, based on our load changing or the voltage dropping that's coming in, the output of the op amp will actually increase. Okay, so that's our regulation right there. We have a stable reference and we're comparing it to an output. This makes this a closed loop system. On the other hand, if the voltage output increases, we get a larger voltage at the non-inverting terminal and the output voltage of the op amp drops down. All right, again, that's our regulation in action. So how do we control the output voltage? Well, we use what are known as pass transistors. Now, I'm using a lot of pass transistors in parallel because I'm trying to draw 25-30 amps. Okay, so we want to equally divide the amount of current between these transistors. These are the ones mounted to the heatsink. So if I'm drawing 30 amps on my load, then I divide that by 5, I get 6 amps per transistor, which these particular ones are analogous to 2N3055s, which can handle quite a bit of current. Plus we have forced air cooling and a pretty big heatsink. Now I cannot drive those directly from the output of the op amp because if I recall, the LM324 can only provide like 30 or 40 milliamps per channel. So we're using a Darlington transistor here. These are two transistors basically in series, and they provide a lot of current gain. So I don't need to drive it very hard. Okay, this guy does all the work. So now back to why did we choose 6.2 volts, okay, as a reference when we're trying to get an output of around 13.8 volts. Well, since we're using a non-inverting op amp, if you recall, non-inverting op amps have a gain greater than 1. So their gain is dictated by this formula, okay? Gain is equal to 1 plus resistor 1 divided by resistor 2. So it's always going to be greater than 1. In this case, I chose to double it with a gain of 2. So the voltage at the output of our regulator is going to be Vout is equal to 6.2 volts for our Zener diode multiplied by 1 plus the ratio of these two feedback resistors. Okay, so 1 plus 10K over 10K is equal to 2 inside parentheses multiplied by the 6.2 gives us about 12.4 volts out. Now you're saying, hey, didn't you still want 13 volts? Yes. So I can actually throw a variable resistor in between these guys, and I can vary that output voltage by kind of manually changing the ratio of these two resistors, okay, just by turning the screw. And that gives me like a couple of volts plus or minus this right here. So that's essentially how it works. So before we actually solder everything to our blank PCB, let's just breadboard it first, make sure it works, and then we'll connect it to the high current supply that we've made. Right now it's just connected to a power supply for testing purposes. So again, 24 to 25 volts coming into our breadboard. That's powering both power rails. So the heart of everything is the LM324, or you could use a 741, any garden variety op amp. Our voltage reference is our Zener here, which is reverse biased. We have our 1K current limiting resistor for that. The inverting op amp, the negative feedback loop, is connected to this string of resistors right here. So I have two 10K resistors and I have a 10K potentiometer in the center of that. So I can change that voltage from about 10 to 20 volts. The output of the op amp is driving this Darlington transistor. In this case, I'm using a TIP 121, TIP 121. So the output of the op amp drives the base of that. The collector is connected to the positive rail of our raw 24 volts coming in. The output drives the base of our transistor array here. So these things can handle like 10 or 15 amps per transistor. I can't recall off the top of my head, but on the back we have our ballast resistors, which help share the current between all of the transistors. Okay, so let's go ahead and turn it on. 24 volts input. Okay, so we are at 11.5 volts. Let's crank my potentiometer up. We can get a little over 21 volts. So I want it to be about 13.5. So let's turn it down. You know, so I really need 12 volts up to 14 volts is really my spec for what I'm going to use this for. So that's perfectly fine. So now that we've tested this at about 1 amp, let's plug this whole thing into our prototyping section of our power supply, and there we can apply some serious current and really test these things out. So this is the Multicomp Pro, MP710259. It's a 300 watt, 30 amp programmable DC load. So the output of our power supply is connected to the terminals on the load, of course, nice and tight. And we're going to start out with, well, actually no load. We're just going to monitor the voltage here. And of course, there's going to be no current until we turn the load on. So this acts kind of like a variable resistor, and we can load down the power supply to the point where I want to back it off, okay, if things start going haywire. I'm going to try to get up to 30 amps. So, first time really turning everything on. I'm a little bit nervous, but here we go. Let's see if it regulates. We are on. We are at about 17 volts. My LEDs are lit up here. That means the polarity is going to the right place, so my capacitors won't blow up. Nothing's hot here. 17 volts is high, but recall that we made this variable. So my inrush current limiting varistors are cool. Don't ever touch the live side of a power supply. I just want to make sure that nothing's going to explode in my face. Ballast resistors are cool. Okay, so we should be able to turn the potentiometer to adjust that voltage down to 13, about 13 and a half volts. We'll say that's what we want. Okay, good, that works. So hey, it works. That's awesome. Now, since nothing has exploded in our face, let's go ahead and draw some current. So this is going to load down the power supply until it draws 1 amp. So 1 enter on. Okay, we're 13.4. So the Zener regulator circuit's doing its job. Our Zener diode is functioning in the reverse breakdown region, and we are dissipating 13 watts in this load. Okay, let's crank it up to 2 amps. Now we're at 26 watts. I mean, that's pretty low for this power supply, so I don't expect anything to be driven too hard. Let's jump up to 5 amps. Fans coming on the load. Okay, 13.2 volts. Let's go up to 8 amps. Dissipating 100 watts, we're at 13 volts. So we're still, I mean, you can see there's a little bit of nonlinearity, and that's because of the Zener curve. So let's go up to 10 amps. Let's beat it up. It's starting to drop a little bit more, which is kind of expected. Okay, let's push it. Let's go to 15 amps. Now we're dropping down to 13 volts, a little under. I deliberately turned the fan off on the power supply so you could hear me speak, so I've got to keep an eye on everything and make sure we're not getting too hot. Ooh, these varistors are starting to get pretty warm. That's probably 60C right there. And let's go up to 20 amps. Let's turn it on. 240 watts. We're at 12 volts. Okay, turn that off. Let's go to 25 amps. Let's get crazy. Ooh, dropping down to 10 volts. Okay, so I'm not really sure what's going on there. So let me do a little bit of troubleshooting here. All right, I've got the fan on now. I thought, maybe we need to keep these transistors cool, but I think that the issue here is, I know I've drawn more power with those transformers. I think the issue is the op amp. I just looked up the data sheet. The spec says its current source capability is 40 milliamps. So yeah, I'm just gonna have to figure out or put a different transistor in there with a higher current gain, or find something else to buffer between the op amp and that. Another transistor possibly. So at least for now, it works. I'm monitoring the voltage across the Zener diode, and let's see, we are drawing 21 amps at about 12 volts, which is still within the specification, which I set for myself. And yeah, 6.8 volts. So Zener as a voltage regulator works. Who knew? All right, well, that wraps up this project. I hope this helps you understand Zener diodes a little bit better. One of the things that everyone's probably screaming about that knows anything about electronics is you probably wouldn't want to just use a single Zener diode in an application that wields this much current. There are solutions out there in an integrated circuit that can control past transistors for you. Which is what I'm eventually going to do, is replace that Zener with a proper linear regulator. So we still need to add overvoltage protection, overcurrent protection, some thermal protection for the transistors. So there's some more stuff that needs to be done. So yeah, that op amp's going to come out. A linear regulator is going to go in its place to control everything else. But the point of this video is kind of to back up the theory of the previous video we did on Zener diodes. So I hope it fills in the gaps and shows you how you can use it in an actual real world application. So anyway, don't be shy. Hit me up in the comments down below. As always, engage with us in the Element 14 community. The links are down below, and I will talk to you there. All right, have a good one.